if we have a graph of pressure P versus volume V for a gas, then in a typical expansion we might have an increasing volume and a decreasing pressure, so that's, this segment of a curve might represent a part of an expansion. The area under this curve is approximately equal well, in a sense it is equal to the average pressure times the change in volume. Okay? This is a rectangle, a trapezoid actually, and if you find the average altitude of the trapezoid multiplied by the width, you get a pressure multiplied by change in volume. The units are units of work because pressure is in newtons per square meter, volume is in cubic meters. When you multiply newtons over square meters by cubic meters, you end up with a meter here times the newton, which gives you a newton meter. And that is, of course, a unit of work. To see a little more precisely why this is work, let's consider a piston, kind of a crudely drawn piston here, but we have a uniform cross-sectional area A. We have a piston in a cylinder. Now, if the piston is moved out distance delta x, then since there's a force exerted on the piston by the gas, the force exerted by the pressure, in fact, the gas does work as the piston moves out, and the work will equal the average force exerted by the gas against the piston times the distance delta x. Now, relating that to change of volume, the change of volume is the product of the cross-sectional area and delta x. The average force is the average pressure as the piston moves from here to here, and if it doesn't move very far, that average pressure will be close to any pressure, multiplied by the area. Okay, so average force is average pressure multiplied by area, so that the amount of work done, which is average force times delta x, can easily be seen to be equal to the average pressure times your delta V. That is, if you wish, your average force is average pressure times A, so that's average pressure times A. Your delta x is delta V divided by A, so if you multiply average pressure times A by delta V divided by A, you get average pressure times delta V. So that is your work, and that certainly makes it plausible that work is the area under the curve. And of course, if you take limits, you realize that you get the work. If you form Riemann sums and take limits as the mesh of the partition goes to 0 and so forth, you find that the work is in fact just the area under the curve, which is the integral of the pressure function with respect to volume. Again, each term of your Riemann sum is going to be average pressure, some representative pressure within the interval, times the delta V. You add all those up, take the limit, and you get the integral of P dV.